Welcome back to the final lecture in ECE 501B for fall. The project deadlines 2 and 3 are due today. I guess you don't have a second project, do you? That could really put some stress on, and we don't need any more stress. Teacher course evaluations are due tonight at 11:59. I really would appreciate a high percentage of students filling those out so that I get the full breadth of the class. And our final exam is scheduled and will occur in this classroom on Tuesday from 6 o'clock until 8 o'clock, and that's in the evening, not in the morning. So that's 6 p.m. to 8 p.m. next Tuesday.
We are giving perks for other classes for doing teacher course evaluation.
You're getting what?
Perks.
Perks? Well, I didn't have to offer perks, and I already had most of the class filling out TCEs, so we will see what happens with the perks. I'm going to give you a final. How's that? So the perk for filling out your TCE is a final exam, which is required anyway, but just to keep us all in the know, I am trying to maintain office hours, but I really don't have too many scheduled between now and our final. I have one tomorrow from 3:30 to 4:30. That's the normal. My one on Friday is right in the middle of my other final exam, so I will not be in my office on Friday, this Friday. So we're making up for that with an extra 2-hour time slot on Monday morning from 10 a.m. until noon. So those are the office hours that are adjusted or modified versus the normal semester. The final exam, its process will be very similar to what you've seen in previous exams, except now you get a few more pages of notes. I think that's an extra page maybe from what you had in the second midterm. But bring something if you need to calculate. I don't know that you will. Definitely bring something to write with, but that's about it. And you will not need a blue book to complete this. Apparently the bookstore is providing those free of charge. I won't even ask you to bring a free blue book to the final. You can write on the pages that are provided for the final exam. Our goals today are to finish the second textbook, which means what I'm really going to do in this list is sort of lay out the order or the sequence of topics that you could now progress through, and then we will see how far down this list we will get today. But this set of goals is obviously more extensive than what we will cover in today's class, but this sort of gives you the big picture view of how you can now progress through that book, or how it will lead you through this infinite dimensional material relative to what you've already seen in the yellow book, or that's the second edition of Axler, or the finite dimensional case. Now instead of vectors, we are talking about signals. And now when we start thinking, how do we have different vectors, now we want to partition these signals. And we partition these signal sets to give us a way to distinguish or associate functions with each other. And that will lead us into equivalence sets or equivalence classes. And so now we have these equivalent signals that we can think about. Once we have those, we can start talking about a distance. And that gives us a metric. How do we maybe measure the distance between functions? Between vectors, we had a way of sort of finding a vector's length. Now how do we sort of talk about a distance or a metric for functions? And that's then what, once we define a metric combined with a set, then we can have a metric space, so that we now have signal spaces instead of vector spaces. I mean, you could call it a vector space, it's just now our vectors are signals. Once we have these concepts of a metric space and distance, now we can talk about how close are things getting to one another, or their convergence. And once you have convergence, you can also talk about continuity. But convergence actually means that we can start talking about a Koshi sequence. How many have heard of a Koshi sequence? Maybe not, but now it's essentially looking at how pairs of these functions, how close together these pairs of functions are getting. And obviously, if something is converging, you would think as these infinite sequences are approaching their limit, you would think that two that are close to each other, that are approaching that would be close to each other. And a Koshi sequence deals with how do these pairs of sequences of functions, how do they move, or do they get close to each other? And if you have a converging sequence, then you know that those will also produce a Koshi sequence. But the reverse is not necessarily true. A Koshi sequence does not necessarily imply that you will converge to a function in your original set. But we can then, once we have convergence, we can talk about Koshi sequence. I just said that we might have a case where it might be a Koshi sequence, but it may not converge to a function in our set. And if that's the case, then our set would not be complete. And that we then say if we have a complete metric space, we mean that the space is complete if every Koshi sequence goes towards a limit or a function or converges to a signal in that space that we are starting with our Koshi sequence. If we're talking about an infinite sequence of functions that are converging or convergent, then we are meaning that that sequence limit belongs in the set. And here's just a slight note in blue. If we do have a convergent sequence, then obviously that implies that we could find a Koshi sequence in that set, but the opposite or the other direction is not necessarily going to hold. We could have a Koshi sequence, but that doesn't mean that where they are going will actually be a function in our set of functions. So the limit may not belong to the set. And we are going to start giving some examples of these sets of functions. But as I said, this list is pretty long, but this essentially gets us through the first, let's say, 5 chapters of that second textbook as far as what is being covered. And maybe as you move forward in your career in this direction or others, you might start hearing some of these phrases. You might hear of a separable metric space. Now we can essentially cover this, let's say, set with a countable covering. And you could think of the real axis or the real line and now looking at little covering sets around particular points on that real line. Again, thinking about covering, the first one was a countable covering. So now you could say a countable set, you could think of the natural numbers, and that sort of just goes on and on. A compact metric set says that that's limited to a finite covering, so that now you have a bounded covering of this particular set, and it's countable. It's finite. Not necessarily countable. Countable means essentially then you're going with this counting numbers or countably infinite. That's another way of sort of thinking about countable. Compact means it's a finite covering. What did we do in vector spaces? We started looking about spans and what's linearly independent, what isn't. Then we could talk about these addition and scalar multiplication. We can do the same thing with functions. How do we add functions, and can we then introduce scalar multiplication? That now gives us linear spaces with this infinite dimensional setting. And that allows us then to talk about independence and subspaces. We can then introduce a norm, or this concept of length. How do we get the length of these functions? If our set is complete, which means that all converging sequences end up in the space that we started with, then we have a Banach space. And that's a complete normed linear space, and we just keep progressing to more and more sort of fine grained spaces. We could then introduce an inner product to give us this angle in addition to maybe a distance or a length. We can talk about an angle. And what's an inner product do? In terms of, let's say, thinking about the final exam, when I start mentioning an inner product, what does that involve? Two vectors. And those two vectors now are collapsed into a scalar. So we can do the same thing with these functions or with these infinite dimensional spaces. How do we combine or connect two functions and produce a scalar? That's our inner product. And if we can find an inner product, a valid inner product on these spaces, that gives us this concept of an angle, but it gives us inner product spaces. If everything in that space converges to a point in that space, then we have a Hilbert space, which is a complete inner product space. I don't think we will get there, but an example might be a time ambiguity function, meaning how different is this waveform, or how far apart is it if you translated that waveform in time with itself. So if it changes a lot, if you shifted that waveform, then you would like to think that you could measure that and say, oh, those two functions are quite far apart. If an original function compared to a time-shifted version of that function, how ambiguous is that waveform if it's translated, let's say, in time? And then we could talk about signal representations, where we might have now basis for a signal space. Once we have a basis, can we talk about those functions being orthogonal? And if we now have those with inner products, we can start talking about orthogonal, and we can start using that norm or that inner product to give us a norm, and the norm can allow us then to normalize these vectors to give us orthonormal basis, to allow us to produce something that we've already done in the finite dimensional case, is this Gram-Schmidt process. So you can continually sort of add up or add together these different vectors. So let's look at the first part of this long list of goals, which was to start with signal sets and start thinking about partitioning and getting into signal spaces. So let's look at these first four sort of ideas to begin with. And that's under this heading of signal spaces. The first thing that we want to talk about is thinking about sets of signals. What kinds of signals could we be referring to, or could we collect into certain sets? Let's then look at sets of signals. And to contrast that with where we've already been, we can relate that to what did we start with in the first part of Axler? What was sort of the first thing that we started talking about? vectors. So now we're looking at signals, contrasting that with vectors. Recall that in the finite dimensional case, we started with a set of vectors. Now, in this particular part, when we're talking about infinite dimensional vectors, now we will start with a set of signals. Let's just give some examples. Sinusoids. How could we sort of collect all sinusoids into one descriptive expression? So here is our set of subscript s for set of sinusoids. We could say that that's all these functions x. Now x is again overloaded. X is a function. But now we have x such that x of t is the real part of this exponential, where the exponential has an exponent of alpha plus j of 2 pi ft plus theta. And that's true for t, let's say, between minus infinity and infinity, where alpha, f, and theta are real numbers. And what you could do is you could remember Euler. Euler says that e to the jx is cosine x plus j sine x, and we're just extracting the real part of that. What we have here, though, is slightly different from that. Now we have e to the alpha, and we have e to the j, 2 pi ft plus theta. That's really sort of what we're doing by adding those exponential terms. And what's e to the alpha? That's just a magnitude. So that scales or gives us the magnitude of our cosine, and e to the j, 2 pi ft plus theta, gives us, when we take the real part, cosine of 2 pi ft plus theta. That gives us all of our sinusoids that we might be interested in. Alternatively, we could define our set of sinusoids to say s sub s is now all of the functions x such that they satisfy the following differential equation, which is then, let's say, this second partial of x with respect to with respect to t, plus lambda squared x of t equaling 0. And for lambda real, functions that satisfy this second order differential equation will be sinusoidal. And that's another way that we could create a set that consists of sinusoidal functions. What's another possible set of functions? Was that me? Ouch. Okay, so now it could be energy limited. signals. In this case, now we have S sub E, and let's give it an argument of K, where the energy is now limited to a value K. And now we are saying that we are interested in all the signals X, such that the integral from minus infinity to infinity of the square of that function is less than or equal to that value of energy K, where K now, let's say, is less than infinity. That's another set of signals that we could start with or use. What's another possible set? Suppose we said duration limited. Signals. So that now we are saying let's subscript it with D for duration, and now we will cut the signal off after capital T units of time. So that now we are interested in the set of functions x such that x of t is equal to 0 for all values of time t, both positive and negative, that exceed in absolute value that interval of time, capital T. And what that's saying is that these x's are now 0 outside of this time duration of 2 capital T. Now, if I take an x that's duration limited, and let's say that that x is in the set S sub d of t sub 1, and then I say, oh, x is an element of S sub d of t sub 2, or let's say that x, if it's in S sub d of t1, implies that it's in the set of signals that are time duration limited by t sub 2. What's the relationship between t sub 2 and t sub 1? So now I could flip a coin and get either greater than or equal to, or I'm sorry, greater than or less than, right? But which one do I want? If x is in this duration limited signal of t, capital T1, and it's also in this duration limited, or that implies that it's in S sub d of t sub 2, what's my relationship on t sub 2 and t sub 1? And if we can't really see that, maybe we could just sketch something. Let's say that we now are saying that our waveform, let's say this is now x of t. Here is t. We now are saying that x of t is in that time duration interval. Where is t sub 2? It needs to be beyond that, doesn't it? So now t sub 2. So this is true as long as t sub 2 is greater than or equal to t sub 1. So you could now have these sort of collections of sets, all based on the duration or the length of duration of different functions. Now that we've talked about time duration limited, we could also talk about frequency limited signals or band limited. And now let's say that it's S sub B, and let's say the frequency that we are restricting content to be inside of is frequency omega, where now we have this set of X such that capital X of F, let's say that's the Fourier transform of our waveform, so that's this minus infinity to infinity of little x of t e to the minus j 2 pi f t dt. We now are wanting that integral to be 0 as long as, or when, the frequencies exceed this, let's say, upper limit omega. Or if we now plug in f's that are beyond little omega, then we're saying that that integral over all time is going to be 0. So this, and what's the argument of that integral telling us? What do you see now when you look at that integral? Does anything sort of jump out at you when you look at that integral and that argument for this band-limited function? What is that integral, or what could that integral represent? Fourier transform, but what's another way that we've talked about seeing that or interpreting that? If it's now two functions, let's say x of t is a function a, and this complex exponential is another function b, or its conjugate. So now that's not quite a convolution, but it's more like an inner product, isn't it? We're turning out a number, which we want to be 0, when we correlate sinusoids of some frequency, let's say little f sub 2, that it is greater than omega. Now we're saying that that x contains no frequency content at that particular frequency, or doesn't contain that frequency f sub 2, because it's not at all correlated or connected. There's no sort of similar direction in terms of frequency content for f sub 2. And we could sketch a picture of that also. It's now we have our horizontal or independent axis is our frequency. We now might say that our frequency content, and now let's not worry about the absolute value of x, let's just take it to be and now what we've said is that beyond plus omega and left of minus omega, we are saying that x of f has no frequency content. This is just sort of telling us what frequencies are present in that particular signal, little x of t. That's what capital X of f is telling us. Now that we have those sets, we can start to, well, the first time you learned about sets, here's a set that contains apples and oranges and bananas. And here's another set that contains grapes and bananas. What did you think about relative to those sets? What kinds of operations did you sort of first start thinking about when you started thinking about sets? Union and intersection. And we can do the same thing for these sets that we've now identified. Here we can apply set operations like the union, and that union is not giving away blue books. That's not the student union. That's the union of two sets and the intersection. And I don't believe there will be any automobile accidents at that intersection, but we just need to be careful with these intersections. But we can apply that now to these sets of signals, or signal sets. As an example, what if I take the intersection of S sub d of t with S sub b of omega? So now I'm saying, what's the intersection of a time duration limited signal or set of signals with bandwidth limited signals? And now this relies on your intimate understanding of signals and systems and maybe Fourier transforms. Or can you think of a waveform that's time duration limited? Think of a pulse. And what's the Fourier transform of a pulse? Do you remember that? In terms of frequency, do you remember it being sort of this sync waveform? And what's how many frequencies are in a sync? Not in the kitchen sink, but in this sine x over x function. So it goes on and on to infinite. So we cannot actually have a time duration or the set or the intersection of the set of time duration waveforms and the set of frequency limited waveforms. That's actually empty. We can't have a signal that is both duration and time limited and frequency limited. So this actually is the zero signal. Or this is now the set of functions x such that x of t is equal to 0 for all time. And because you may not remember that until you look back at your notes, let me just write out what I tried to say. The only signal that is both band limited or has a limited bandwidth, or only so many, or beyond a certain frequency, there is no frequency content above that. The only signal that is both band limited and duration limited is in fact the zero signal. That's what that's trying to say, and I tried to remind us of what that, or one way of maybe thinking about that. Recall the Fourier transform of a finite duration pulse waveform, where relative to time, here's x of t, there's t and minus t. Let's say that's now our duration limited waveform. And what kind of a What did x of f look like for that? That was this kitchen sink. No, not the kitchen sink, but the sine x over x waveform that just kept going and going. So if you have one, you can't have the other. For example, if I now said I have a sinusoid of a particular frequency, what does its Fourier transform look like? It's now two frequencies, isn't it? Or a positive frequency and a negative frequency, or two line spectra in the frequency domain, only at that single frequency. And that one you could say is band limited, but it's not time duration limited. It's going on and on for all time. So that's sort of the other waveform. A non-trivial signal, and that a non-trivial signal is any signal that's something other than zero. A non-trivial signal cannot be both time duration limited and bandwidth limited. So now we have these sets of signals, and we could start combining those into unions or intersections or other ways of combining sets like we've combined sets in the past. Another way of thinking about these sets of signals, can we actually partition those or sort of keep certain sets of signals identified as being equivalent or similar? And that leads us then into this concept of, can we actually partition sets? For example, let's say the set of sets, here is our set inside this curly brackets, and inside the curly brackets are several other sets. If we now have such a collection or a set of sets, that set of sets is, we will say, forms a partition as long as this pairwise intersection of these sets in that set is empty. So this set of sets forms a partition of the underlying set if we have the following. S is equal to S1 union S2 union all the way down to S sub n if S sub I intersect S sub j is the empty set when I is not equal to j. And now we could start sort of drawing clouds again, couldn't we? Maybe. Here is a cloud, and we could say, here's a partition, here's another partition, here's another partition, so that we might have, this might be S1, this is S sub 2, S sub 3, S sub 4, and S sub 5, to graphically think about this set of sets. Yes?
Is there no direct sum equivalent in set?
So now the question was, is there no direct sum equivalent in sets? We sort of have that here. So I don't know that we have a shorthand notation for that. This is sort of shorthand enough, maybe, saying S1 union instead of the plus sign inside a circle. So here we're talking about sets, and now S1 is a set, and in the direct sum decomposition for finite dimensions, we had these subspaces, didn't we? That we now could maybe say, oh, this subspace plus or direct summed with this subspace, etc. That collection would then complete a subspace or an overall vector space. If we do have a partition, that partition neatly divides a set. There's no sort of overlap between those sets within the overall set. Often it's easiest, or the easiest way to get a partition is via an equivalence relation. Now let's define what we mean by an equivalence relation, and this will be now related to functions, where we're now saying these functions are elements. So two elements are equivalent if x wiggle y. That's what we're notation. That's the notation that we are using. That this squiggle or is a wiggle, and that is what we're saying is equivalent to saying x equivalent to y. So x wiggle y, or x is equivalent to y if we have x and y satisfying the following three conditions. If x is equivalent to x for all x, b, x is equivalent to y implies y is equivalent to x for all x and y, and finally we have if x is equivalent to y and y is equivalent to z, then that implies x is equivalent to z for all x, y, and z. And that's what we will use to define what we mean by two signals or functions being equivalent, that they satisfy these three conditions. And there's an infinite number of ways that that can be done. There are an infinite number of possible definitions of what makes two elements equivalent. The rule for equivalence just needs to obey those three conditions, A, B, and C. The rule just has to obey A, B, and C. And if we now apply this idea or concept of equivalence, or apply an equivalence rule, then that gives us equivalence sets or equivalence classes. Application of an equivalence rule creates equivalence sets or equivalence classes. Where we might have a set sub x, or now we have this equivalent set, S sub x is the set of all functions y, such that y is equivalent to x. And these equivalent sets or classes, the equivalence sets allow us to form a partition of the, let's say, overall set. Or we could go the other direction. We could define a partition or partition our set, and that would then define equivalent sets. Also, any partition defines an equivalence rule. Let's see if we can create some sets with equivalent sets or partition those. Here's one example. Consider the set of integers. So here is our set, and we want to create sets within this set, but our overall set S are the integers. Let's say those are now n, such that n equals 0, plus or minus 1, plus or minus 2, etc. Now, can you think of a way to partition integers? Minus 2, minus 1, 0, plus 1, plus 2, plus 3. What's a way to maybe cleanly partition integers? Evens and odds. So now if we said something like, let's just do modulo 2, separation of these integers, or let's say mod 2 congruence, now generates 2 equivalence sets within this original set S. So that now we could say S1 is now this equivalence set or equivalence class of n equal such that n is equal to plus or minus 1, plus or minus 3, plus or minus 5, etc. That's the odd set. And then we have S sub 2, that's the set of n such that n is equal to 0, plus or minus 2, plus or minus 4, etc. There is our even set. And that now, S sub 1 and S sub 2 partition the underlying set or the overall set. So now we have sets of a set, or a set of sets, where the sets are S1 and S2, and our set is the set of natural numbers. What's another way of creating a set of sets. Suppose that we consider set of all signals except for a zero signal, where we will define this zero signal, S sub 0, to be the function's x such that x of t sub 0 is equal to 0. Is it clear? And here t sub 0 is 1 point in time. It's not all t. So now I've just identified, or basically extracted from all of my signals, this particular zero signal. I'm saying let's not consider that to be 1 in this collection of signals. This now represents, or is made up of, the signals that in fact equal 0 at t equal t naught. Now, do you see how we could partition the set of all signals to create a set of sets? What our maybe 2 sets might be? Now we can actually define so now we can define, I apologize for that delay, but I had to sneeze, so if you noticed a pause, that's what it was. We can now define a partition, and I really apologize if I didn't turn off the microphone soon enough and that sneeze actually came through. I'm sorry for damaging your ears, but hopefully I turned it off soon enough. But now we can say we could look at a set that's the positive set, or the set of signals x, such that at t naught these signals have a positive value. And we have another set that we could say is S negative or S minus, which are all the signals x, such that x of t naught is negative. So if this is how we've defined S plus and S minus, we could actually define an equivalence relation to determine whether 2 signals are equivalent. If I give you 2 signals, you could say, do those signals belong to the same set? Are they equivalent? Meaning, if I give you an x and a y, could you now come up with some way of determining whether those 2 signals are equivalent with each other? And they don't have to be exactly the same waveform to be equivalent, do they? This partition can be used to define an equivalence rule. Meaning, again, if I give you an x and a y as functions, can you tell me if they are equivalent? Not if they are in S plus or S minus, but are they both in the same set? Let's see if this makes sense. Suppose that I now say x is equivalent to y if x of t naught times y of t naught is positive. Is that an equivalence rule for this partitioning? So now all you have to know is if I give you a signal X and a signal Y, to see if those two signals are equivalent relative to this partition, you just want to know, are they both in one of these sets? So that now you say, just tell me what X is at T naught and tell me what Y is at T naught. I'll form that product. And if that product is positive, then I know that they belong to, or they are equivalent relative to this partition. They're both either in plus or they're both either in minus. You don't need to tell me that. You just need to tell me that they're equivalent, that they both belong to S plus or they both belong to S minus. And this should do it. That's an equivalence rule. Because if they're both in S plus, at T naught, they're both positive, so the product of positives will be positive. If they're both in S minus, they're both negative, so the product of two negatives is positive. So this does allow us to create an equivalence rule as a result of this particular partition of a set of signals. Let's look at an example of this. Suppose now we want to, or somebody gives us some waveforms or functions and they want to know where do we put those. So let's now say that here is our time T naught. And now maybe I will give you a waveform that looks like this. There's, let's say, F1. Let's say that F2 is there. F3 and F4, oh, that's supposed to be, well, it doesn't matter. F4. Can you, based on this drawing, and maybe we are really only interested in these waveforms between some limits, A and B. As long as A and B are containing T naught, we can use this set partition. Now, is it clear where these belong in terms of sets? F1. That belongs to S plus. What about F sub 2? That's also S plus. F sub 3. Can we say anything about F sub 3? What it belongs to? If you evaluate or look at the value of F sub 3 at T naught, it's now negative, isn't it? So this is going to be S minus. And what about F sub 4? It's S minus also. And we can now say that F1 in this, using those two sets, is F1 equivalent to any of the other waveforms? And by equivalence now, I'm just saying, are any of these sets in both S plus, I'm sorry, which signals belong to S plus and which signals belong to S minus, those will be equivalent with each other. so that F1 and F2 are both in S plus, so F1 is equivalent to F sub 2 using our definition for S plus and S minus. And we can say that this is true based on that equivalence rule also, where we had F1 of T naught times F sub 2 of T naught, and that indeed is zero, or positive. What about F1 and F sub 3? Are those equivalent? No. So now I'm just going to make up a notation. Let's put a diagonal line through the wiggle. So we now say F1 is not equivalent to F sub 3, and that's consistent with our equivalence relationship. We can see that the product of F1 at time T naught and with F sub 3 at T naught is actually 0 and not positive, and so those are not equivalent. Now you can also define an equivalence set from one of its members. Note that equivalence sets or equivalence classes can be represented by a characteristic member, let's say x hat. Meaning we could say, oh, the set sub x hat will be all the set of functions in our underlying set such that x is equivalent to x hat. And it really doesn't matter what you pick for x hat as long as it belongs to your set that you're wanting to identify. This does not matter your choice of x hat. So now we have defined sets of signals. We've talked about how to partition those. Let's now look at the next idea in that list, and that's signal spaces. And once we start talking about spaces, now we want to start introducing a concept of distance. We have sets of signals, or we have signal sets. We want to combine that with distance, or some way of defining distance, and that will now give us a signal space. Just like with vectors, we like to know what's the length of that vector, for example. We introduced a notion of length. Here, a distance let's say definition D is referred to as a metric if the following properties hold for that definition D. A, if D of x and y is greater than or equal to 0, and the only time that D and x and y is equal to 0 is when x is equal to y. So if you take two functions, x and y, then their distance is non-negative unless they're equal, and then it will be 0. The distance, or the metric for d of xy, needs to be the distance or the metric of dyx. So we need both a, b, and we need also c, that the distance between x and z is actually less than or equal to the distance between x and y plus the distance from y and z, where this last relationship we can think of as a triangle inequality. What are some ways that we could define distances for functions? Suppose that we now said d1 of xy, and now the subscript 1 is significant because now we're going to be looking at sort of the argument of this integral being raised to the first power. So that now let's say that we're dealing with functions between a and b. Let's say now we define a distance between x and y as the absolute value of x of t minus y of t raised to the first power dt. And really we could sort of say, oh, let's take the first root, or, it's not a square root, it's now not really even a root, but you'll get the idea relative to what we will be doing with subsequent d's. So here, this you could see referred to as the L1 metric. What about d sub 2 of xy? And now we can try to use the 2 where we have had a 1 in the earlier definition. So now the distance d2 between xy is this integral between a and b of the absolute value of x of t minus y of t squared, and then square rooted. So that this is now the L2 metric, or you might see this as the Euclidean distance between x1 and x2. Another distance, which the book actually I think uses subscript 3, maybe I'll use infinity, I haven't decided, I haven't written it down yet, since I assume you can see how those additional integer distances might be defined. Let's now say that we have d sub infinity of xy. This is now the sup of the absolute value of x of t minus y of t, and sup, now you're getting hungry, I shouldn't have mentioned sup at this point in the lecture, but sup is the supremum, or this is now the least upper bound. It's not a maximum, it's a least upper bound, because we may not actually achieve the maximum. And we don't want to just say it's an upper bound, we want to know what's the smallest upper bound. In terms of a picture, maybe that would help. Suppose that I'm now sketching x of t minus y of t, where maybe that looks like the following. Let's say this is now time. What I'm trying to differentiate with relative to the sup and just an upper bound, do you see that that's the least upper bound I have, let's say this is now 8, and let's say this is 4. Maybe I shouldn't have said 8. That looks too much like an infinity on some angle. So let's just say this is 7. Is it clear that 7 is an upper bound of the difference between x and y? And so is 4, but 4 is the least upper bound. So 4 would be the sup, which is the least upper bound. 7 is an upper bound. But it's not the smallest. Yes?
If we are writing like d2 equal to x y, we are raising to the power square and then a square root. But instead if we are replacing with infinite, then don't you think that it will always be 1 because we are ultimately raising to the power 1 by infinite, it will be 0.
So now we're looking at the supremum of the difference between x and y. So if x and y, we're looking over all time, and we're looking at the absolute value of their difference, we would just be pulling off the least upper bound of that difference. So that could be any number, but we're needing it to be bounded in order for this distance to be meaningful. So it just needs to be some finite number, the difference between x and y at some point in time. Maybe most of the time it's that difference between x and y might be less than 7. But then, whoa, at one instant, maybe it jumps up to 20. So that now the sup of that absolute value of the difference between x and y as a function is 20. When the 2 norm or the Euclidean norm might look more like an average difference between x and y in terms of it's now looking at this absolute value squared, integrating that, and then taking the square root. So that's looking more like an averaged value of the difference between x and y. The sup allows us to basically capture the largest when this 2 norm may not be bigger than the largest difference between x and y, because we're averaging that out over all time. Whereas the sup is just capturing that the least upper bound of that largest difference. Now, if we combine a set with this distance, then we will have a metric space. So a set of elements, and now you can think of a set of signals, sinusoids, bandwidth limited, duration limited, etc., a set of elements plus a metric. Now you could combine that with the sup metric, the D2 metric, the D1 metric. A set of elements plus a metric is a metric space. Let's say that's S, comma D. Now what you want to know or keep in mind is that we could start with the same set and pair that up with a different metric, and we will have a different metric space. So the same set, but a different metric, meaning we could have D1 or D2, then that's going to lead to a different metric space. or if T was our set of signals, then we might combine or pair up T with a D1 distance. We might set up or pair up our set of waveforms T with the Euclidean distance or with the soup distance. Those three pairs of sets and distances are different. So they each make their own metric space. These are different metric spaces. Now, if we had a few more minutes, we could cover the rest of the material. But now we're up to talking about convergence and Koshi, etc., but we now will have to stop at getting you up to this idea of putting distances with metrics. Then you would start thinking about norms and inner products, etc., to give you Banach spaces and Hilbert spaces, so that if you start hearing those, you sort of have some idea what you're talking about. Good luck on the final, and that's when I will see you next, unless I see you during office hours.